Yeah, thanks a lot for the RTU letting me to present in front of you. So I will make a short update on a field we are focusing on, and just in case there is somebody in the audience who doesn't know what Nvidia is all about, we are world leader in visual computing. But if explain where are we focusing on, we are focusing on three major directions for us. So it's PC, mainly for gaming. You probably know us as a company doing the great GPUs for video gamers. Second direction is data centers. So we have a wide range of products for data centers, from GPU accelerators to the virtualizing solutions, and I will briefly talk about both of these. And the third direction is mobile. And mobile is basically everything between smartphone and your car or your future car. There are some common themes which unites all these directions, and I will talk about this a little bit later. I would start from the accelerated computing, and basically in our case, accelerated computing is built around the Tesla computing platform. But for the moment, Tesla became a wide platform for different type of IT technology specialists, domain specialists, researchers, and scientists, because it includes now not only the hardware and necessary drivers and stuff like this, but it also includes the language necessary for making or adopting your applications. It includes the tools to manage the product, which could be inserted into data centers, and so on and so forth. So it's the whole ecosystem built around the idea to let you and other users accelerate their codes or applications by adding GPU into the system, and as well as using the right version of the application which can benefit from the GPU in the system. The big focus now for us is in the field of deep learning, and the deep learning is actually here for already many years. The basic principles around deep learning have been invented back in 70s last century, but only recently it became feasible for not only for researchers but for commercial companies to use deep learning for something meaningful, for basically for business, for making money, for making some research, and so on and so forth. So the four reasons to change the importance of deep learning recently basically are: there is lots of data available now, and deep learning is all about your training set on which you use to train your network to make some judgment. And data is all around us. So you already heard about about the Internet of Things, Internet of Everything, and so on. But even without going to this, so the number of videos available on YouTube, the number of messages we send using the Facebook and all other social media, social tools are huge. And without this, and this actually, this data allows to make some sophisticated learning algorithms smarter, and basically allow researchers and the companies using this to use this for some cool things. So this gives the ability to make better models, to make more sophisticated networks. And recently GPU entrance into this area let researchers and commercial companies to efficiently use deep neural networking hybrid clusters using GPUs. There are already multiple examples, but probably one of the obvious things is the image recognition. The image recognition was there for many years, but it was dedicated algorithms, handcrafted to try analyze the picture and find some faces or some objects, but just slight change in this picture and this algorithm no longer works. So deep neural networking is totally different. So as long as you make your network smart enough and feed with as much data as possible, you can get pretty decent results. So first of all is image recognition and all the related things to image recognition. And now, just back in February, the machines beat the human's capabilities. So now machine can find some predefined object on a random image with a higher accuracy than the average person can do. So this is pretty important, and this basically opens many other opportunities related to the image recognition, from the text recognition to the autonomous language translation, and so on and so forth. So how it looks like? So you build the multi-layered network, and when you give some inputs, when this input goes through the different layers, at the end of the network, you could receive the meaningful answer. In order to make it working, once again, you need train this network on as much test sets, as much data as you can, and that's why the availability of social networking data, the stream videos, the data from different kind of sensors is really what makes deep neural networking works and let people make some significant results using these techniques. There are many examples from totally different areas, like for example Spotify, which is the service which lets you recognize the music. You just get the couple of seconds from the music, and it defines what this music is, even in a noisy environment with a bad quality of microphones. It allows in the field of medical imaging, it allows to find some patterns related to some diseases on medical images, and basically there is nothing revolutionary in the idea of this, because now this work, and for already many years, this work is done by highly skilled medical personnel. But the thing is that automation of this process allows you to make this service publicly available for wider areas and for more people than before. And of course, some breakthroughs in terms of the drug discoveries using this technique. So if you look for the let's say big internet giants, starting from Google to the Apple to Baidu in China to Yandex in Russia and many others, they all use deep neural networks running on GPUs in production. So, for example, if you get your phone and say, "Okay, Google," and then tell something, you will immediately get the text out of this. So this is the easiest example when you touch deep neural networking on the GPUs. And there are many others. What's next in terms of deep learning? So we believe that deep learning will be almost everywhere pretty soon. So starting from the autonomous driving cars in probably next 5 to 10 years, basically the deep learning will be the backbone for the visual system of the car. So the car will be able to recognize the environment around the car and drive or help you either self-drive or help you to drive more safely. And this also allowed to make this solution cheaper, because now many expensive cars has some advanced driver assistance systems, but it's built on very expensive radars and other sensors. So basically, sophisticated computer vision algorithms allows you to make this solution cheaper and switch to using the more cheaper just regular cams by providing the sophisticated algorithms to analyzing the inputs from these sensors. Now let me switch to kind of different topics, because I spent some time on the deep learning and GPU computing ecosystem. Now let's talk about the people who use who basically applies their mental skills to make all these things happen and write the applications. So if you look for the application, in order to get this accelerated on a system with a GPU, you need to make some efforts to get your code running efficiently. And there are two ways to make it happen. So first of all, if you already have some code, and especially if this code heavily uses some public, widely available mathematical libraries, then probably the best way to get speed up with this application would be basically change the libraries, basically naming of the libraries, to ones which already adopted to the GPU. And there are many different libraries in different segments available. So if you're looking for the kind of quick copy-paste, I would call it copy-paste acceleration, then probably using the library would be the first choice. The second option is using the directives. And there was kind of big discussion around this. So directive is there for many years. So for example, if you look for the OpenMP, it's here for, I don't know, for more than already a decade for sure. And the OpenACC is basically kind of extension of this approach, which lets you get your code running on a system with a GPU without going deep to the code optimization. So now let me spend some time on this. So the OpenACC is kind of the same idea as OpenMP. So basically, you add some hints for the compiler, which part of the code should be moved to the GPU, and you let the compiler do some smart job on this instead of you spending time on this. This is basically gives you the simplicity, so you don't need to spend much time on optimizing the code, especially if you are not the programmer, but you are rather domain specialist. So this lets you keep your code stable. You don't need to make the few versions of the code. You can add directives, you can remove it. So you need to keep only one copy of the code. And it's pretty powerful tool. So here's the example of Cosmo code, which is used in Swiss Meteor Agency. So it's been ported by using OpenACC approach, and there are some statistics on this. So the part of this code, one of the models from this code, contains 60,000 lines of code. Only 5% of this code has been basically touched by adding directives. And as I mentioned, it allows the developer of this code keep only one copy of the code, so no need to track the many other versions. And there are speed ups mentioned below, which was achieved by this approach. So different models has different acceleration, but the thing is that was the only small amount of time has been spent to get this speed up. There are some few other examples what's possible with using OpenACC. But don't get me wrong. So OpenACC is not the magic tool which lets you do almost nothing and get speed up for free. But the thing is that OpenACC gives you the opportunity, especially being domain specialist, get your code accelerated without being specialist in parallel programming. So here's the example. So I've took one of the applications which already been parallelized using OpenMP, and just on top of OpenMP we added the OpenACC directive to get this code running on a GPU system. So once again, it allows you keep only one version of the code without worrying that this insertion will affect the code. And here's what you will get. So same code running on a single core of CPU. That's fine. Then we add OpenMP with 16 threads. Then we OpenMP with 32 threads. Get some decent speed up. And then on top we just add directive for the OpenACC. So, and on top of this we are getting 2.5x speed up from what's achievable by OpenMP. So this kind of the speed up on speed up. And once again, you didn't spend any time on changing the logic of the application and changing the algorithms of the application. Now the question is, I've told you that OpenACC is powerful. The question is, how is powerful? So here's the performance report from one of site which we are partnering. So they make some comparison on a few rather simple examples of the efficiency of OpenACC versus the highly optimized parallel code using the CUDA extension. And you will see that on average, you will get roughly 80% efficiency from what you can do by hand coding, which is not that bad. Especially once again, I would repeat it many times that this is the approach for the domain specialist. If you don't have enough experience in adjusting your code or reworking your code because you are specialists in, for example, molecular biology, not the parallel programming, then probably OpenACC is the way to go. Of course, it's always better to spend some time on a hand coding and some tuning, but there are not that many specialists in this area, and especially in cross-disciplinary areas when they have decent knowledge in some special field as well as in parallel programming. And what's important that you can program your code or your application on a regular PC or laptop on workstation, just using the GeForce widely available GPU. And when you need to move to something bigger or to something more reliable, then you just get your code running on a dedicated hardware and it will work as it should without spending any extra time for adjusting your code, moving from one product to another. In terms of roadmap, so we are currently here, and if you look for our roadmap actually back, so we are about to launch the 6th generation of successful products. So we started this back in 2006, and since then, despite of the different comments from the industry, each of our GPU generation for computational task was more successful than previous, and basically all these products could be found in pretty big installation across the globe. But of course, there are many things we need to improve, and especially it was mentioned in the beginning today, and it's mainly related to the power efficiency of the overall systems, and especially if we talk about the big systems. And our next product based on the Pascal architecture will have some major improvements to overcome issues related to the power, and at the end of the day is not the power itself but the efficiency, meaning the number of computations we can do using the fixed amount of energy. So our current product is Tesla K80. I would not spend much time on here, but this is the just basically fastest accelerator in the world with the biggest amount of memory, widely used across many different scientific centers, and especially good for deep neural network related research due to the highest performance for the single thread as well as the, sorry, not the single thread, single precision as well as for double precision. If you compare the performance of this product in the applications which could run on a CPU as well as on GPU, you would find that across the scientific and real-world application domains, this product is roughly 10 times faster than just a regular CPU. And if you look again for our roadmap back, then you can find that GPUs way faster than the regular CPUs. But the thing is that this gap between performance of GPU and the CPU, as well as the performance of memory subsystem on a CPU and the GPU, is becoming bigger and bigger. But actually, there is a threat in this, because GPU could work only together with the CPU, and if this gap becomes too big, then your performance could be dismissed by interface between CPU and the GPU. And in order to overcome this issue, our next generation product called next architecture called Pascal will have a few major improvements, and one of them is NVLink. So this interface, which will let us overcome limitations of existing PCI Express. So this interface will be 5 to 8 times faster than the current generation of PCI Express. And what is really important, this interface will let us connect GPU between each other as well as the GPU and CPU. So this will be the major improvement in Pascal generation. And another big thing that starting from the next generation, our products will use 3D stacked memory, which allows you to increase the amount of memory available for the GPU, as well as the speed between GPU itself and the memory chips. And also important thing that the power efficiency of the stacked memory is almost 4x higher than current VRAM, which once again, all these improvements mainly targeted for improving the power efficiency of the product itself, as well as the system based on this product. Despite of the fact that this product will come only next year, you probably recently heard that two next biggest systems in US will be built based on this architecture and the architecture which comes after this one. So there are one system I would like to point you out which will be installed in 2016 called Summit. So the peak performance will be in a range of 100 and 300 petaflops. Despite of this fact, it will consume exactly the same amount of energy as current Titan system consumes, and this will 1/5 of the size of the current Titan system. So we are pretty well on track to get the level of exascale in 2020 time frame. So this system will be built on a power CPUs from IBM with integrated NVLink interface, as well as the GPU based on the upcoming architecture. What is important that this system is basically will be built to tackle really important problems in the field of medicine, in the field of new energy sources, and many others. So this system, this performance of the system should really help scientists and researchers to make next breakthroughs in their fields of research. One more thing I would like to touch is, just a second. One more thing is that, especially when you look for the system of such a size, the amount of computations and modeling you are doing is really huge, and sometimes the problem is that even if you get the results, you need to somehow interpret them. And in many cases, the good way to do so is basically to visualize what's been calculated. And using the GPUs in the system basically allows you to use exactly the same hardware and do it in parallel while you keep computing your let's say your math or physics. The system lets you visualize on the fly, so you don't need to have a dedicated visualization system. You can reuse same resources. And in order to do so, we are partnering with the companies doing the libraries and the tools for visualization. So you could check with the Kitware their products, for example, which lets you visualize on the fly your simulation. And the last thing I would like to touch is not related to the HPC, but related to the cloud, and probably related to the previous talk, is the virtualization of the graphics. We recently, basically a year and a half ago, introduced the new product line called Grid, which allows to put the GPU in the cloud. Which means that the people can have same experience using even heavy engineering applications like I don't know, AutoCAD, CATIA, SolidWorks, and so on, but without having the powerful workstation under their desk. They could basically get connected to the cloud, to some data center, and get same level of performance and experience while working from their light-weighted laptops or even tablets. What's the benefits of this? So first of all, it's accessibility. So any kind of users, despite of their graphical needs and performance needs, can get access to their workplaces basically from anywhere with sufficient internet connection. So it's really easy to scale. So if you now need only 10 people working with an application, you can get 10 virtual seats. If you need 5 more, it's just a question of few minutes to get more virtual machines running on top of existing GPUs. And in terms of IT department, it's way easier to manage one data center instead of hundreds of separated workstations across the company, or especially in case where the company is saturated across regions, time zones, and countries. I think that's it that I have from my side.